Hi, I am Shakil Hussain Shah. My advisor is Professor Fujan Kao. Today I will discuss about photon counting based stimulated emission palm probe microscopy. Here is the outline. Now over past few years world is undergoing a quantum revolution. We can observe advancements in the fields of quantum computing, quantum communication, quantum sensors, etc. Here figure A shows the first commercial quantum computer deployed by IBM. This computer is based on quantum computing. Quantum computing is an area of study that is focused on development of computer based technologies which are based on principles of quantum mechanics such as superposition, interference, entanglement. Quantum communication is the method of protection of information channels, as here is public channel and quantum channel, against external interference through quantum cryptography. In simple words, quantum cryptography describes the use of quantum mechanical effects for coding and decoding of data. And the next is quantum sensing, which is an advanced sensor technology. It detects changes in motion and electric and magnetic fields by collecting data at the atomic level. This sensing method also uses quantum mechanical effects. If we are interested to know that how basically these photons interacts with atoms and molecules, we should focus on quantum optics. Quantum correlation is the expected value of the product of alternative outcomes. We can understand this concept with a simple experiment. Here the source S produces pairs of photons in opposite directions towards right and left. Now each photon encounters a two-channel polarizer, and emerging photons from each channel are detected, and their coincidences are counted by coincidence monitor CM. After detection, we can see its results. For example, n++ shows the number of simultaneous detections, which means it shows that the both photons are detected at the same time. We can define photon anti-bunching as a light field with photons more equally spaced than a coherent light field. Here we can see photon detection as a function of time. For example, light emitted from a single atom, that is here by green, and this shows a coherent state laser beam. Here the photons are not single, but these are in pairs, and also these are dispersed. And this one shows the bunching, that is in thermal light field, where the photons are in collections. So we cannot expect single photons in these two cases. Only photon anti-bunching can provide us single photons. Now here are a few types of photon correlation experiments. In one-dimensional correlations, a beam splitter distributes the incident beam between two single photon detectors. Then arrival times at these detectors are correlated. In multidimensional correlations, multiple single photon detectors are used, as we can see here, to allow parallel detection along another dimension such as energy. Due to replacement of beam splitter in first case with dispersive elements, optical setup became more simple, and there is reduced signal loss. The third one is photon correlations in imaging. So we can also use photon correlation in time and space dimensions to achieve background noise rejection, improved sensitivity and resolution. For example, this figure at the bottom is a super resolved image of a biological sample. This sample is acquired using spatial temporal correlations. And figure A shows here the basic HBT setup to measure autocorrelations at the single photon level. So here beam splitter evenly distributes the light emerging from a single photon emitter between two low noise single photon detectors, these two, and the purpose is to measure the light's second order correlation function g square t. If only one photon is emitted at a time, simultaneous detection will not be occurred, and the detector output have no correlations, as we can see here. It means no photon pairs, so no coincidence. Secondly, according to figure B, if we observe a group of quantum emitters, we can count their number by using a technique that is called COPS, or counting by photon statistics. Actually, if multiple excitations are weakly interact, as here, so number of active emitting centers could be estimated by photon correlation analysis. For example, by using this COPS, it is possible to count up to 30 fluorescent molecules within only 0.5 seconds. Next one is about a complex emitter has multiple emissions and multiple emission centers. So excitations from these emitters can jump from one center to another center. For example, if we two identical emitters, these two are supposedly identical emitters, these are connected by a molecular bridge here. So we can estimate the probability of their recombination process, that how they recombine with the help of correlation function. Figure D shows that in some specific semiconductor nanocrystals, anti-bunching could be controlled according to the shape and size of the particle. If at least one of the particle dimension is larger than Bohr radius, then mutual interaction strength is reduced because their electron hole separation is increased. So in this case, the probability of photon pairs is increased. So as we can see here, and the next one is about multidimensional photon correlations. So photons are correlated across time delay in their arrival times, and here an additional property, the delay between excitation and photon arrival time, these are also measured. So we can see here in figure A that a two-dimensional correlation between these two properties, and then applying a correlation analysis, we can get the gated anti-bunching. And here these two figures show that gated anti-bunching G square T rapidly decreases with increasing gated time. So the reason for this decrease is non-radiative relaxation or dark transitions. Second case is about sequential measurements. So in this case, photon are emitted from excited calcium atoms, and these are passed through a linear polarizer. These are tunable filters. So before each of two single photon detectors. Now in these experiments, two polarizers are either parallel or perpendicular to each other. So photon bunching peak at 0 time delay. Here at 0 time delay we have this anti-bunching peak. So this is observed for parallel polarization, not for perpendicular polarization. And now these sequential measurements mostly take much longer time, so parallel measurements are used to overcome this deficiency. Here in this figure, a diffraction grating is used to map photon energies to different pixels of this pixel detector. This allows parallel characterization of both the time of arrival and also energy of each detected photon. So applying this method to semiconductor quantum dots enables measuring the doubly excited state spectrum within a few minutes. That is a fraction as compared to the previous two methods. So in this way the parallel measurements are mostly much effective. Now there are various techniques for imaging with the help of using this photon correlations concept. In figure A. If we are able to observe whether photons are arrived at same time or not, we can step forward towards super resolution capabilities. So figure A shows one of such approach where an object is illuminated by spatially correlated light and it's imaged onto EMCCD camera. Estimation of the frames as compared to these correlation functions, we can get the estimated results. A next technique is based on confocal scanning, where correlation function between pairs of photons is calculated for every scanning step. That is, after each scanning step, the correlation function is calculated. Now here the zero delay dip, it serves as the contrast for this imaging, and we can clearly observe that as compared to generally used scanning microscopy, this quantum scanning microscopy can give much better imaging resolution and contrast enhancement. Next one is we can get phase information by measuring the photon coincidence rates. As compared to classical illumination that is shown in figure A, B and C, quantum illumination in D results in phase enhanced imaging. So we can get much better imaging results. And this last one is about quantum illumination based on AND operation. In this technique, a simple pixel by pixel AND operation only keeps the photon pair events, and it rejects most of the uncorrelated events that arise from sensor noise or unwanted background illumination. Hence, much better images with noise and background reduction could be observed. As we can see here, the images obtained with quantum illumination and operation are much better and clear as compared to classically acquired images. Our future work is aimed to realize quantum enhanced anti-bunching, and hence the expected results could be helpful in biomedical applications, including real-time tissue engineering, diagnostics and drug delivery. Thank you for your attention.